Hi, I'm Herb Gross, and welcome to Lecture 12 of Gateways to Algebra, where today we're going to look at a very special relationship called linear relationships. And they're special for two reasons, almost opposites of one another. The first is we're starting with linear relationships because they're possibly the simplest relationship that one can handle analytically. But the stranger part is that as simple as it is, it's also the building block for handling the most complicated situations and are, in a sense, used as a prelude to calculus. But before we get into that, let's show how easy it is to describe a linear relationship. Let's look at a fairly simple program here. We have an input, we multiply by 12, we add 5, and we write the output. For example, if the input is 6, we multiply by 12, gives us 72. We add 5, gives us 77, so the output would be 77. If the input were 7, what would happen over here? 7 times 12 is 84. 84 plus 5 is 89. So if the input was 7, the output would be 89. Doesn't look too profound, I don't think yet. If the input is 6, the output is 77. If the input is 7, the output is 89. Now, let's try to think of a real-life situation where this might come up. Let's suppose there are people coming over for a working session. I'm going to have coffee and donuts. I want to make sure I have enough donuts for the people. So I go out and I buy boxes of dozen donuts. Now, let's suppose in the house I have 5 donuts. I go out and I buy 6 boxes of donuts. How many donuts are there in each box? There are 12. So 6 times 12 is 72. I'm therefore buying 72 donuts. I already had 5 in the house, so 72 plus 5 would be 77. Of course, if I went out and I bought another box of donuts, 7 boxes instead of 6, each box has 12 donuts in it, so therefore it would seem that what? Every time I increase the input by 1 dozen, the output is going to increase by 12 more donuts, so the fact that we went from 77 to 89 is no great surprise here. In other words, notice that this step over here, multiplying by 12, guaranteed what? That every time the input increases by 1 in this problem, the output increases by 12. Now, by the way, it didn't have to be donuts. I could have been buying pens, and there could have been 12 pens in the box. Or I could have been buying an expensive pastry at $12 a pound and $5 for shipping and handling. There are all kinds of examples where you could take what? The solution would be pick an input, multiply by 12, add 5, and write the output. And what's interesting about this is what? Every time the input increases by 1, the output will increase by 12 in this problem. And that's called a linear relationship. A relationship is linear if whenever the input increases by 1, the output always increases by a certain fixed amount. In this case, the fixed amount was 12. As we'll show later, if you were multiplying by 3, the fixed amount would have been 3. But the important thing is what? Changing the input by 1 will always change the output by the same amount. And let me show you now where the word linear comes from. Very often, what we do in mathematics is something like this. We use the argument that a picture is worth 1,000 words. So rather than talk about input and output, we take 2 number lines. This is going to lead to something called graphing that we're going to talk about in more detail later on. See, what we say is, why can't we, see, in other words, when we're given a relationship, why don't we just match an input with an output? And what we'll do is we'll measure the input horizontally and the output vertically. Let's see how that works in this particular problem. See, what's happening here is what? We're saying what? Let's look at this as the input-output will be the donut problem in this case. This is the number of boxes of donuts we buy. There's going to be 12 in a box. And this is the number of donuts. Now look what happened. When we started, we had what? We didn't buy any boxes, but we still had 5 donuts in the house. So in other words, when we buy no boxes, there are 5 donuts. See, what we're going to do is we're going to list the horizontal, the input first, followed by the output. See, when the input is 0, when there are no donuts that you're buying, the output is going to be 5. Now you buy 1 dozen donuts. What does that do? You buy 1 box of donuts, Now you have what? The 5 plus 12 more, that gives you 17. And the way we write that is 1 comma 17. See, we're always going to do what? We're going to put the input first and the output second. See, this is read what? When the input is 1, when you buy one box, you're now going to have what? 17 donuts. Now you buy another box. So now you have what? 2 boxes. And how many donuts do you have? The 17 plus 12 more is 29. So you see what we're doing? We're drawing a picture over here. And can you see what's starting to happen over here? Every time the input increases by 1, the output increases by 12. So you go 1 over, 12 up, 1 over, 12 up, 1 over, 12 up. Isn't this going to be just like a staircase? In other words, can you see this? When I draw this, it's going to be a straight line. That's where the word linear comes from. And by the way, I want you to get used to the idea of an input and an output, the idea of writing down an ordered pair. Notice that 2 comma 29 does not mean the same thing as 29 comma 2. See, the input comes first, the output comes second. In fact, didn't we study another relationship earlier in the course? Remember, is the capital of? Suppose you write down blank is the capital of blank. You see, what I put into this blank affects what I can put into this blank. If I take, for example, Boston and put it in here, what should come over here? Massachusetts. See, the first member of the pair is Boston, the second member of the pair is Massachusetts. You're not going to say Massachusetts is the capital of Boston. It's what? There's an order here. See, Boston is paired with Massachusetts, Sacramento would be paired with California, Albany would be paired with New York, Raleigh would be paired with North Carolina. And you see the concept of ordered pairs transcends mathematics. But what's nice about ordered mathematics is that when you have the ordered pairs, what you can do is what? You can basically look at a curve which is more intuitive. See, people have an easier time visualizing a picture than they do looking at numbers. For example, have you heard expressions like profits rose? How can profits rise? Only way profits rise is if you throw the safe in the air or the office safe blows up. Profits increase or decrease. What we're saying is what? If you have the increasing direction being upward, when the profits are increasing, what does it look like? The curve is rising. You see, it becomes a version of a picture is worth 1,000 words. See, we look at the picture. In fact, if you want to see more of the point of what we're doing, remember we said that arithmetic was when you had the input and the program, and you wanted to find the output. Algebra is when you had the output on the program, and you wanted to find the input. What we're doing with graphs is, when you know the input and the output, can you construct the program? See, sometimes by looking at how the inputs and outputs match up, you get a picture that suggests a program. But the idea is this, though. The thing to remember is most relationships are not linear. For example, when you're twice as old, you're not usually twice as tall. We'll come back to that in a little minute. The generation gap very frequently happens because people forget that life is not linear. Meaning what? The person who's been on the job for 20 years thinks he's 20 times as smart as the person who's been on the job for just 1 year. You see, people do what? They confuse 20 years of experience with 1 year of experience 20 times. See, just because you're twice as old doesn't mean that you're twice as smart. Just because you've been there twice as long doesn't mean that you've had twice as much experience. And so what happens is sometimes a younger person comes in, does all sorts of things, but the older person says there's something wrong with this. He can't be doing all these things right because he hasn't been here as long as I've been. See, we always assume certain linearity, even where linearity doesn't always exist. I mean, let's go back to this height thing again. For example, you're born at a certain height. And as you get older, especially when you're an infant, the height increases quite dramatically. Then you grow at a slower and slower rate. Eventually, your height tapers off. And I guess there are some theories that say past a certain height, you even shrink a little bit. Okay? So here's the height graph, hardly a straight line. By the way, I think I mentioned to you at the beginning of this lesson that calculus is concerned with applying linearity. See, for example, look at this curve I just drew over here. Even as badly as I draw, you can see that this is not a straight line. This is not a linear relationship. But I use the cliche, life is locally linear. What I mean by that is, let's suppose near a point that I'm interested in, I draw a line that's tangent to the curve. Tangent is just a geometry way of saying, and we'll refine this later in the course, that just touches the curve. Do you see the intuitive thing of what a tangent line is? Can you see how that line just touches the curve over here? Here's the thing. Do you notice that, say, from about here to here, you cannot distinguish the tangent line from the curve itself? In other words, even though this curve is not a straight line, from here to here, it's pretty well approximated by a straight line. Of course, the further out I go, the worse the approximation becomes. But at any point, can't I just draw a new tangent line? And so close to each point, I can do what? Find a linear approximation. And basically, that's what calculus is doing. But let's go back now to the idea of a linear relationship in more detail, because I want you to get to be good at being able to handle linear relationships. Let's go back to our donut problem again. The input was the number of boxes, so we took the number of boxes, we multiplied by 12, we added 5, and we got an output. Now, of course, it didn't have to be donuts. The input could have been anything. Let's call that x. We didn't have to multiply by 12. We could have put 13 in the box. We could have put 6 in the box. We could have put 3 in the box. Let's just call the number we multiplied by, let's just name it m as a constant. See, we multiplied by m. Okay? Now, we didn't have to add 5. We could have had 7 donuts at home, 15. What we really did over here is what? We added some number that we had at the beginning. See, I used m to stand for multiply. Let b stand for what we had at the beginning, and then the output will denote by y. So in the traditional algebra format, a linear relationship has the form y equals mx plus b, where m and b are specific constants that depend on what the problem is. This is a very nice, simple form. And what's interesting is that if you give the commands input, output, add a constant, subtract a constant, multiply by a constant, divide by a constant, if you use these steps over and over and over again, you could put 500 of these into one problem. This will always keep regenerating a linear form. In other words, when you get through simplifying this, this will always come back to the mx plus b form. For example, suppose we start with x, multiply by 2, add 3, multiply by 4, add 5, and then write down the answer. Remember what we said. To be linear, it has to be what? Multiply by a number, and then add a number, and that's the end of it. Okay? But watch what happens over here. You start with x, you multiply by 2. That gives you 2x. What's the next step say? Add 3. Okay? What's the next step say? Multiply by 4. The 4 multiplies the 2x to give us 8x. The 4 multiplies the 3 to give us 12. Do you see what's happened? When I combine these 3 terms, simplify it, what does this say? This says what? Pick a number, multiply by 8, and add 12. Isn't that the linear form so far? But we still have one more step. It says what? After you've done this, now you even have to add 5. Well, 12 plus 5 is 17. And now what happens is this program here now looks like what? Start with x, multiply by 8, add 17, and the answer is y. You see, does this have the linear form? This says y is equal to what? 8 times x plus 17. See, and this would be what? The 8 would play the role of m, and the b would play the role of 17. And what this tells you, by the way, is in this program, and I'm not going to take the time to verify this, but you can, or maybe I will take the time, we'll see. What this program says is every time the input increases by 1, the output is going to increase by 8. Well, let's just try it and see for the heck of it. If this is 1, I multiply by 2 gives me 2, add 3 gives me 5, 5 times 4 is 20, 20 plus 5 is 25, so if the input is 1, the output is 25. What should the output be if the input is 2? If my conjecture is right, the output should be what? 8 more, because this says what? Every time x increases by 1, y is going to increase by 8. My guess is the output here should be 33. Let's see if that's the case. Start with 2, multiply by 2 is 4, add 3 is 7, multiply by 4 is 28, add 5 is 33. See, even though this didn't have the mx plus b form, did the rules of my game allow me to paraphrase it into that form? And in this form, do you see how much I can recognize that might have been obscure here? All I want to do for the rest of this lesson is to make sure you recognize linear forms. For example, is y equals 3x plus 7 linear in x? What does the form have to be linear in x? It has to be what? Y equals mx plus b. Well, compare this with this. M is 3, b is 7. In other words, does this have the form start with x, multiply by a number, add a number? Yes. The number you multiply by is 3. The number you added is 7. This is linear. And what does that mean, more importantly? It means every time x increases by 1, y will increase by 3. See, that's the key. An increase in 1 in x will always lead to an increase of 3 in y because m is 3. By the way, look at some technicalities over here. Is y equal 3x linear in x? See, to be linear, what form does it have to have? mx plus b. Well, we have the m over here. Where's the b? Well, don't we have a rule that says when you add 0 onto a number, it doesn't change it? Isn't 3x the same as 3x plus 0? So now does this have the mx plus b form? Yes, m is 3 and b is 0. And again, don't get hung up on the mx plus b form. That's just a convenient way of writing it. The important thing is what? Every time x increases by 1, y is going to increase by 3 here. And that's an easy one to check, isn't it? See, what happens here? When x is 1, y is 3. When x is 2, y is 6. When x is 3, 3 times 3 is 9. When x is 4, 4 times 3 is 12. And you see that every time x increases by 1, the output y is increasing by 3. That's the importance of the y equals mx plus b form. Here's another one. Is 7 minus 3x linear in x? Wow, that looks all funny. First of all, the x term is after the constant term, and there's a minus sign in here. See, how would we read this? Start with x, multiply it by 3, and subtract that answer from 7. See, x, multiply by 3, subtract from 7. Wow, that doesn't look linear, because to be linear, the form had to be what? Start with x, this part's okay so far, multiply by a number, but the next step was supposed to be add a number, not subtract from. But watch how this works. Let's apply the rules of our game. This is 7 minus 3x. One of our rules said what? To subtract, you could always add the opposite. So 7 plus negative 3x is the same as, 7 minus 3x is the same as 7 plus negative 3x. This is now an addition problem. In an addition problem, can you add in any order you want? Yes, it's commutative. So we can now write this as negative 3x plus 7. Now do we have the mx plus b form? Yes, m in fact is negative 3 and b is 7. And by the way, the fact that m is negative simply says what? Every time x increases by 1, the output is going to decrease by 3. And doesn't that make sense? Since you're subtracting, the more you subtract, the smaller the amount left is. And one way of reading this problem is let's suppose you have a credit at the store for $7, and you're buying an item, and that item costs $3. Every time you buy one of those items, what does your balance at the store change by? It decreases by $3. You buy one item, you've used up $3, you only have 4 left. Buy another item, you only have $1 left. Buy another item, and you owe $2. You see, the negative simply tells you what? That as x increases, y is decreasing, and all that means geometrically is, in terms of the graph, that the height is falling as x increases. Okay? Here, is x plus 4 linear in x? What form do you need to be linear in x? It's not enough to have an x over here. There has to be what? An m multiplying the x. Well, what number can you always assume is multiplying something if no number is there? 1 times x is always x. Therefore, all this says is what? X plus 4 is the same as 1x plus 4. This is linear with m playing the role of 1 and b being played by 4. And all this tells you is what? Every time x increases by 1, x plus 4 also increases by 1. Here's one that's a little bit tricky. This one says is 2x minus 7 linear in x. To be linear in x, what form does it have to have? something times x plus a constant. This is minus, isn't it? But don't we know from our rules that 2x minus 7 is the same as 2x plus the opposite of 7? Therefore, m is 2 in this case, and b is negative 7. This is the tricky part. Don't say that b is 7 in this problem. B is what? See, you only read this number if there was a plus sign over here. See, since there was no plus sign over here, to make that a plus, you have to change the sign. And basically what this says is you owe $7 before you even start this problem. You're already $7 in the hole before anything else happens over here. Okay? By the way, you may wonder why I say linear in x. It's to name the variable. See, is 3t plus 4 linear in x? Well, how can it be linear in x? There's no x in the problem over here. Obviously, the variable I'm talking about is t. So we don't say 3t plus 4 is linear in x. We say what? 3t plus 4 is linear in t. And what does that mean? It says what? Every time t increases by 1, 3t plus 4 will increase by 3. That's what linear means. And again, sometimes we put the thing even into a more complicated form. Here's one that says, is this linear in x? Well, this is complicated, but can we use the rules of the game again? The 7 is multiplying the 2x plus 3. So 7 times 2x is 14x. 7 times 3 is 21. So now we've replaced this by this. Now I can regroup by the associative property. This was the distributive property. 21 plus 4 is 25. So what's the synonym for this expression over here? This says what? If you pick a number, multiply by 2, add 3, multiply by 7, and then add 4, it's exactly the same thing as if you pick the number, multiplied by 14, and added 25. The beauty is that in this simplified form, we see something that may not jump out of this right away over here, and that says what? In this expression over here, every time x increases by 1, every time x increases by 1, the output is going to do what? Increase by 14. Okay? Now, we should conclude, I guess, with an example that shows you that not everything is linear. Let's look at 3x squared plus 1. Is that linear in x? Well, you have an m over here, you have a b over here, but what's wrong with this? Do you notice that in the form to be linear in x, there was no square? Now let's go back to the basic definition. If this were linear in x, every time x increased by 1, the output would always increase by the same amount. So let's make a little chart over here. Let x be 0, 1, 2, 3, 4, 5, 6, and let's see what happens over here. Okay? First, we're going to have to square the x. So 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36. Then we have to multiply by 3. 0 times 3 is 0, 1 times 3 is 3, 4 times 3 is 12, 9 times 3 is 27, 16 times 3 is 48, 25 times 3 is 75, 36 times 3 is 108. What do we do next? We have to add on 1. And by the way, when we do that, if this were linear, what should happen? When x increased by 1 over here, the output increased by 3. So if this were linear, when x increases by 1 again, this would have to be what? Increased by 3. This should be a 7, but it's not. It's 13, isn't it? So does this tell us right away that it's not linear? See, it's not linear because even though the input keeps changing by 1, the output keeps changing by bigger and bigger amounts. And by the way, we're not responsible for this in this course, but don't think that just because something isn't linear, that there still aren't nice things that one can do with this. Let me show you something that you'd have no way of understanding, but I just think it's kind of interesting. Look at the 3 here and the 2 here. If you multiplied those together, that would give you 6, wouldn't it? You say, big deal, what's that got to do with anything? Well, I thought I'd like to show you something to conclude today's lecture with. Look at these numbers, 1, 4, 13, 28, 49, 76, 109. They're increasing faster and faster, aren't they? It's not changing linearly. In other words, as we move down the list, the change becomes different. Let's see, from 1 to 4, what's the change? 3. From 4 to 13, the change is 9. From 13 to 28, the change is 15. From 28 to 49, the change is 21. From 49 to 76, the change is 27. And from 76 to 109, the change is 33. Now let's do the same thing again. The change from 3 to 9 is 6, from 9 to 15 is 6, from 15 to 21 is 6, from 21 to 27 is 6, and from 27 to 33 is 6. And in fact, if I did it again, all the differences would now become 0. And this is called numerical analysis. It's called successive differences. And what I'm saying is, even though we're just dealing with linear expressions, the thing that's really interesting is that looking at patterns, applying the rules of the game, never comes to an end. It's like playing any other game. When you start playing chess, you usually make a lot of mistakes. As you become better and better at it, you make fewer and fewer mistakes. Your level of sophistication increases. Same with any kind of a game. And math is no exception that way. As we master one level, we move on to the next level. So what we've done is we've now entered into the game of mathematics, the game of algebra, by starting our first serious investigation of a particular type of algebraic relationship called a linear relationship. And the next several lessons are going to dwell on the concept of linearity. But we'll get into that piece by piece, lesson by lesson, and if we do it right, there won't seem to be that big a difference from one class to the next, because we'll be moving what? Just one little step at a time, but cumulatively the result will be great. At any rate, work hard, have fun, stay young.